Hello everyone, I wanted to share something today. I've been playing around with packet encoding in Godot specifically, and I've been looking into how to decrease the packet size and improve the encoding of whatever I'm trying to send over the network. So this video will basically apply for any networking, anywhere where you need to send data over a network. But in this case, I'm using it in Godot. For that, I've just made a basic scene to have a bit of a context of what we're doing. So we have this character that we can control around with WASD, and we are pretending as if we are sending the inputs that the user makes over the network. So we'll encode them on one end and decode them on the other end, and then apply those inputs to the character and run move and slide, which then actually moves the character. So Godot, when you would like to implement something like that, uses their RPC architecture, and that's basically what this simple encoding is trying to mimic. If we go down a bit, this would be a regular RPC function, like move character, and you're given the direction vector, and of course, depending on what you're trying to control or send over the network, you might have several more arguments, and those then, and that's now a thing where I'm kind of speculating. I haven't looked into it. I didn't investigate the packets that Godot actually sends when you do an RPC call. But my wild guess is it puts all of those arguments into an array, and then just uses its var to bytes function and packages up those variables into a PackedByteArray and sends them. The var to bytes function is one you can. It's a global function, and I think I read in the documentation that's actually the function they use to encode variables in Godot, and that they use in their RPC calls. So I think that's kind of a good approximation. And depending how smart Godot is, it might do some optimizations, but I've the feeling it's probably pretty dumbed down, just takes those arguments and encodes them and then decodes them on the other end. So that is what we've done, and that is what we are using here in our little demo. So the question is now, can we improve on that? First we would have to look at how large is this packet, and can we decrease its size? So here I'm just putting some encoding printouts in a ready function, and this is a dummy vector just to give us some data we want to encode, and we're just going to print out the packet and then the packet size, and we'll do that with every iteration of our encoding algorithm that we're going to develop here. So now if we look down here, we see the packet itself, the packed byte array, and the length of 20. So I'm just going to spoil this very quickly. Those last 8 numbers, those are 2 float numbers. You've got your x float number of your vector 2, and you have your y float number. And floats in Godot are encoded as 32 bits. You can also compile Godot as 64 bits, and then you would use doubles that would double that size. But your standard version of Godot has 32-bit floats, and And those are the numbers actually. So if we just want to send like a vector2, we basically just need those numbers. But what is all of this now? So this is basically metadata, because Godot doesn't know anything about this structure. So those, I don't know, maybe like I think 4 or 5 bytes here are just to tell Godot on the other end, hey, those are not just random bytes, but this is actually a vector2. Okay, so we're sending this information over the network as well. So this says this is a vector2 and it holds those values. So what are those bytes in front? Those are our array. Like this is basically just our array metadata. So if we would have more arguments, we would, they would have to be separated, and Godot would have to know that this is actually an array. So we are sending over the network 2 structures, like an array, a vector2, and then we actually send the data. So I think the next idea is, okay, we can dumb this down or simplify this a bit. Of course, every time when we make like packets smaller and more efficient, it means we are sacrificing something. If it's convenience or amount of decoding or encoding that is required. So there are always certain kind of compromises. So the RPC function itself isn't a bad thing because it can just simply handle anything. You just pop in your arguments and it pops out those arguments on the other end. But it's not very, very efficient. So let's take a look how could we reduce the whole thing. So we could get rid of that array and just encode our vector. So let's do that, and let's print out the resulting. Oops, we're skipping ahead. There we go. So this will be dynamic fixed encode. So in this case, at least that was the name I gave it. It's not scientific or anything. In this case, we basically just get rid of the array. And if we would have several arguments, and so on, we would just not use an array structure, but know on the other end where those bytes are encoded and decode them. So in this case, if we look at those at the packet, the size is a lot smaller already, just by omitting the array structure. We still have those x and y values that we found here, and here is our metadata to indicate that this is a vector2 structure. So again, we can improve on that, and it's pretty intuitive. The idea is just to decode the x and y values. Like why even bother with the vector if we know on the other end this is going to be a vector2 that we're trying to send. So Godot provides us with the PackedByteArray class, and that does all the heavy lifting for us, all the encoding. A PackedByteArray is exactly this. It's just an array. It has a fixed size and it's initialized with 0. So you'll probably know that from other like lower level programming languages where this is pretty common. It just makes things a lot faster, easier to compile, more predictable for the compiler. So it's more performant. And so we'll have to resize it to our desired size. We can also use like different functions on that packed byte array. Like if we look at the documentation, this is going to be your friend. So take a look at this, because that'll help you just encoding, decoding stuff, optimizing things. If we would use like an append function, that would do the resizing for us. But if we use like an encode function, we would have to have the space already provided for the data to be written on. And that is what we're doing right now. So we're resizing it to 8. 8 is the number of bytes we are allocating. And we are using 8 because, as we talked earlier, those are 32 bit floats, and 32 bits is equal to 4 bytes. So it's 4 times 8. So every float requires 4 bytes to be able to encode. So, and when we encode, we can set an offset. So we'll basically just think of having like an empty space, the first like 0 values, and we're deciding, okay, we want to start writing our x value of our vector onto starting from the 0 index, and we'll write 4 values. And then we'll say we want to write our y values, but we'll change the offset to 4. Otherwise, we would override our x value. So that is the idea. And once you've written that, you can send off that buffer, that byte array. And we're going to take a look at that now. How does it look like? How does it compare to our other encodings? So yeah, you see how I'm working here. It's very nice to just inspect your packets, and you get a great like insight on how all of this stuff works, and get a great insight on how these functions work. So you can double check and learn quite nicely that way. So if we look at this, that is exactly what we expected. We only have those x and y values in here, as we found earlier as well. So this is really stripped down now. So we went from 20 bytes that we're sending over the network down to 8. So that's pretty good, like less than half of the size. So this has been like very basic, very simple. Like all we did was just like stripping out some metadata, thinking about what the sender and the receiver knows about the data, and that is basically it. And I think up to this step, like Godot could do a lot of like optimizations if the user, like the programmer, provides like static hints on what it's actually sending over the network and stuff like that. Godot could probably do that. I don't know if it's doing it. Maybe it is. But now we're actually getting into the interesting part, the nitty-gritty, because we can improve this thing a lot. And that now is like the part where you kind of go into the compromises and into the greater compromises, and that really depends on your game. So now we have to start to think about, what do we want to send over the network? How does our game work? And what kind of encoding requirements do we have to send this information? So in this case, we are just moving our character, and we just have like, I'm just controlling with a keyboard in this case. So I have like my 4 cardinal directions, up, down, left, and right, and my 4 ordinal, so my diagonal movements. So that's very basic data, and of course like standing still, like not moving at all. So those are 8 inputs and 1 standing still input. So that's not a lot of data, and we are sending a lot of bytes over the network to do that. We're specifically sending a vector that is pointing towards something. So let's take a look at. Let's use our trusty paint friend, and like this would be our Godot character. Okay, you see, I'm perfectly capable of drawing a square, and he will have a vector, like depending where he wants to go. Like if he wants to go top right, he'll have a vector in that direction. If he wants to go down, he'll have a down vector. And if he wants to go to the left, he'll have a vector pointed to the left. And this is our center. So we can kind of already like have an intuitive association of this actually kind of being like a clock, you know, like a circle. And in our case of our Godot character, and because we're using like a keyboard and mouse, we only have a fixed speed. So the length of the of the vector doesn't matter in this case. All that matters in which direction it actually goes. So we can start thinking about the direction of the vector just like we would with a clock, and we could divide this clock up into angles. Yeah? So this would be called a polar system. So instead of using like our vector how we are using it right now, we'll have our trusty Godot character here. Let's see if he's just as squished as earlier. Okay, he's a bit more beautiful. And we've got our x and y values here. So we need to send like an x value, a y value. That's a lot of data. So instead of doing that, we could just say, like we have angles here. Like this would be a 45-degree angle. This will be 180-degree angle. So we would just send 45 over the network. That would be a lot less data. Like that would be just one integer. But we kind of need to stray away from thinking in those data types so much, because like an integer, a float, they can hold huge, very like generic values, and we're actually just interested in very specific values in this case. Like for example, if we look at this clock again and look at our 4 cardinal directions, that's kind of our WASD controls, and if we combine them, we have those ordinal values. So this kind of looks like a cake, you know. You can slice them up, and that's how I'm going to treat this. So in this case, we would have 8 total states that we would need to send over the network. So this could be like if we index it with 0. So you get the point. And that would be enough to send it over the network to get this basic movement. And we have one more state that we haven't talked about, and that is the standing still state. So in this case, we would have 9 values that we would be able to transfer over the network. And if we look at those packets, they all have bytes in them. So in this case, we could do even crazier things, but we won't do that here. But we'll use the byte value as our smallest packet size, because it's kind of convenient the way it is set up here. So 1 byte can hold 265 values, or if we start like indexing from 0, we can have the numbers from 0 to 255. So this is the amount of numbers we can encode, but we only need 9 to do this. So that is pretty great. So we could theoretically cut down our packet requirements from 8 bytes to just 1, which is amazing. Like simply looking at where we've started, we've had 20 bytes, and now we have 1 byte. And we'll look into the implementation a bit earlier as well. But like when I came to this realization that we can just do it that way, I was thinking, okay, we still have like a lot of bytes left. we are only using up 9 values, but our byte can provide us with 265 values. So what should we do with those values? And then I was just playing around in my head. Like, one idea was, what if the user was using a controller and using a joystick as an input? A joystick, if you move it around, has a lot like more granular control of the direction. So we could do that. We could see how many into how many slices can we cut this cake and get like a different direction out of it. So the answer, of course, is like we can have 255 slices plus our standing still state. So if we just Google like wait, what am I trying to do? So yeah, we could cut that into slices. 255 values, but the thing that I like to preserve is like those cardinal directions, like the diagonals and stuff. So it would be good if this whole thing would be divisible by 8 in some shape or form. So so that isn't quite divisible by 8, but let's say we could have like 8 times 31. This would be great. Like we could have 248 slices here to slice up our cake, and that would be like a really nice resolution that we would have for a joystick player. The question is, like, at what point does he notices that those are like distinct directions and isn't like completely like fluid in between? Like, I think 248 slices is probably more than enough. So that would be like for every like small for every eighth of the circle, it would be like 31 values. So that's a ton. I can't even draw that much. So I don't think the player is going to notice that. So this is a really great resolution, and that is perfectly enough. And then I was thinking, okay, now that we have such a great resolution here, could we do something else? Like, can we divide those bytes up into something else? So we could, what if the joystick player would be able to control the speed? Like if we push us down more, the character would go faster or slower. So if we want to do that, we add basically another dimension. Like the first dimension is the direction. Or in this case, we could consider this as an angle. Or a slice. Yeah? And if we add another dimension that we call speed, if we look at if we think of our vector again, the speed would be like the length of our vector. So if we would have a vector here, this would be like full speed as the length 1, and then we would have half speed because the player doesn't push down on the joystick that much. That would be a second kind of speed. But we would have to have these kind of states for every direction to encode them properly. So that's why I talked about dimensions, because a dimension always is always multiplied. So here we have our speed, or when we talk in vectors, that would be our length. Or if we just take this analogy, you could also like think of this whole thing as like circles. like rings on a cake, and every ring is like a gear. So you could have ring 1, and then you have another vector that goes up to ring 2. So that could be like 1/3 of the speed and 2/3 of the speed and max speed, something like that. So you have different amount of speeds, different amount of gears you could have with your character, and you could have different directions. And just for sake of this video, we're going to try to stick all of that into one of those bytes. So that's kind of the idea that I had, which kind of makes this whole thing interesting to me, and hopefully somewhat useful to you guys. So we need to share this space, and I've already played around with it a bit, and I've just decided, okay, I would like to have 40 slices or directions, because it's really nicely divisible by 4 and by 8. So we'll kind of keep those cardinal directions, and the only thing that would be able to fit, like if we have 40 slices and divide that by 255, we would only be able to have 6 gears or speeds, and that would use up 240 of our values on our byte, plus one value we are not allowed to forget. That is our standing still value. So we always have to have one value assigned to that. So this is the entire idea behind the encoding. How can we put complex information into basic states and encode them? And for that, I've set up like those slices and those rings. As I've said, I've used 40 and I've used 6. Of course, this would be a 1-byte encoding where we have 256 values. But we can also have a 2-byte encoding, represented as an unsigned integer 16 bits. You can look at those, what those things mean. You can Google them. You can look at them in the PackedByteArray documentation. Those are pretty standard across most programming languages, or all probably by now. So you can look into that a bit more deeper. But just as an example, if we would just use 2 bytes instead of 1, we could encode a lot more values, like over 56,000. So that gives you a lot more granularity or whatever you want to encode. But for this example, we're just going to use 1 byte and 4 slices for our directions and 6 rings for our speeds. So I've initialized some variables here. Those are not important right now. We'll look at them later. Most important thing, we are getting a direction vector. So we are back into here, living here in this world of this character that wants to move, and he gets a direction. And for us to get those rings, because those rings pertain to the length of the direction, we're just going to take the length. We need a way to, and the direction vector that we get out from our input is always a unit vector, so it always has the length of 1. We could multiply that with a speed. We'll come to that. It would be a fraction of that. If we would go half speed, that would be 50%. But that would be our maximum size. That would be the unit vector. So in order to get the ring, to get the gear that we're in, we just multiply the amount of gears we want to have, the amount of rings we have, and by the length. And that would output a float, but we want to have integer numbers. We're not calculating with floats. So we're just going to round this to the closest float, and that's what we have done here. Now that we have our ring, let's take a look at our slice. We'll look at this when the ring is 0. We'll look at that a bit later. That is basically our standing still ring. So the movement vector is 0. So it has the length of 0. But let's say it has a length, and we figure out in which ring it is. We still have to figure out in which direction are we actually looking or trying to move. So for that, we are going to use, we're going to measure the angle of our vector. And our vector, let's make another drawing maybe. Okay, so we're back here. It's easier, like if we talk about vectors, let's take a look at this. X and Y. So we've talked about our length, and then we have also our angle. So now we're trying to figure out like what is the angle, and Godot does like something. If it is, I'm not sure what I think it's the X and Y. I think it's the X axis. Like this would be like minus 20 degrees, whereas this would be plus 20 degrees. So if you go that direction, it will all be minus, and if you go that direction, it will all be plus. So we don't really want that. We want to have like a continuous angle. It kind of makes it easier to put things into slices. You don't split up the cake into a plus and a minus side. So we're trying to get values from 20, and in this case not minus 20 but plus 340 degrees. Okay, that is what we're trying to do to slice things up. But again, things aren't that like intuitive as we know it from school. So Godot, as I think all math libraries, they use radians. So in radians, that is basically just a floating point number, and that will be equal to 2 of pi. Pi is 3 point something, I don't know. So something like this would represent something like, I don't know, 6 or something, yeah, 6 point ... yeah, as a floating point number. Godot has like a special constant for 2 pi, that would be tau, and we can think of that as just the like an entire rotation on a circle. Like that would be tau, and in this case tau would be the same thing as the starting point of 0. So we can think of the circle as going from 0 to tau, and we're now trying to work with that concept. And here we take the angle that has plus or minuses, and we're converting that to an angle that is only positive, so going from 0 to tau. Now we're doing like very basic math, but I'm really bad at explaining it. I'll just walk you through a bit, but I don't know everything why it works the way it does. But we're essentially trying to figure out how big is an angle of a single slice. And if we have like 40 slices on our cake, we're trying to figure out like what is one of those slices? How big is this angle? Yeah. And once we have that, we can divide it by 1, and that gives us our angle to slice multiplier, which makes things like really easy. Then we just take our angle that we got from our vector, multiply it by that, and we'll get the a floating point number out of the size of or the number or the index of the slice. So if we look at that, this will be like the value of 2 pi or tau. Multiply this with the angle to slice multiplier. So that would be a full rotation. So that would be 32, basically. Like it has some small parts here because it's a float. But that's exactly what we want to get. So if we would have like less angle, this would have a lower value. So, but all within the range of 0 to 32. So that is great. So basically we already have our slices now. All we have to do now is, because our joystick input isn't like fixed integer values, it's floats, and the user can have values in between, like 18 and 19. So we need to round those and convert them into an integer. So we've kind of quantized it, reduced its resolution by putting it into like this bucket into this slice. So everything, in this case, like any user input that would be like close to this slice would be rounded and become like this slice. And that's what we're doing now. And now the actual like kind of encoding part happens. Like this has been kind of preparation, and it's pretty simple math, but you kind of have to do a bit of trial and error until you get the right numbers out. So I had to play around with that quite a bit until I really understood what I was doing. But what we're doing now is filling up this cake. So if we take a look at this cake again, we'll have those rings. Let's say the center thing is the 0 ring, so that is nothing. But we have like the ring 1s or zones, however you want to call it, and then we'll write our first value onto this. So this would have value 1, so it have value 2, and so on until the value of 32. Now the ring is full. We've defined every single state that is available on this ring. Now we'd start writing on the next ring. So 33, 34, and so on until 64. I mean 64, and so on. So we're basically kind of writing every ring with a certain state and slice direction. So that is what we're doing. We have this number 1. That is our one number we need to reserve as when standing still. So that is our 0 value, and so we need to offset all of this encoding. So this is 0 value, and we start with 1. And then we take the slices and the current ring we are in, and then add our slice number to that. I'm not sure if my explanation made sense. I hope this kind of helps. Like this kind of fills up our first pool of numbers. So I've already filled up to 32 or filled up to 64, and then we add the slice that we have, or if it's not filled up, it is 0, and then we start here. So for every number, we have a specific state. Here in this case, I just made this function a bit more variable to be able to encode like 2 bytes or 1 byte, depending how many slices and rings we would have, if it would be more than 1 byte. But in this case, if we were like just encoding like 1 byte, we would have this buffer that we created at the start. And because it's 1 byte, we resize it to 1 and encode a unsigned integer 8 onto it. So this just writes onto 1 byte. If this would be unsigned 16, this would use 2 bytes. If it was unsigned 32, it would use 4 bytes. So we just need that, and offset is 0, and slice on ring, that is our current state, the number of the state of combining of direction and speed. And we encode that and then send it off. So that's pretty nice. We'll have the decode function, but let's take a look if that actually works. So we'll just replace our dynamic encode or RPC encode with the custom encoder and decoder. So this is actually using our function that we have written down here, the custom encode. And voila, this actually works. So this is quite amazing. And we can actually see here in the output what it's doing. You take a look at that. We would have our slice, our ring. Ring would be our gear. So why is it 3? Because right now we have our speed to 5. So if we were to have a joystick, this could be dynamically adjusted. We'll just do it manually in this case. So this ring from 3 should be 6 now if we move. And you can see down here, this is ring 3. So and you can see this character is a lot faster now. And we only have like very basic slice numbers here, like going to left to right. That's very basic, or up and down. So those slices, those values change according to that. And diagonal. So yeah, this basically worked. So this is basically the end of the tutorial or this video. You can take a look at the decode function. It's pretty simple, a lot easier. You can take a look at it. But I wanted to like kind of expand your mind a bit, like not just thinking when it comes to encoding in form of cakes and slices and rings. We can encode a lot of different like domains. Like this could have been a character that we're trying to move. This could be like a 2D spaceship that we're trying to fly around. And you could do different things, like if you want to send like some input from a platform or 2D brawler like Super Smash Bros. Or a fighting game. You could just start thinking about your game. What kind of states do you have? Like what is required, for example, for a platformer, like moving left and right, jumping, crouching, maybe climbing. If that's different from jumping, then you might have an attack. Maybe you can slide underneath things if you move and crouch. Maybe you have a special attack, things like that. So those are all like states, and all of those states we can in the end decode with a single number. So if we look at this cake idea again, those are all just singular states. The cake is just like a thing to kind of help us think about a problem. But it's just about having different states and assigning different numbers to them. So for me, like intuitively, that was like just like thinking of like, okay, we have different movement states. Like you can represent that as an enum, for example. Move left, right, as we talked about. And also like the standing still state, so as a separate movement state. So you can do all those things, but maybe your character has a sword and he's able to do all of those things, but at the same time also slash with his weapon. Then you would have a second dimension. So this would be our first dimension. And then we would have our second dimension. That would be either he doesn't attack, so he just stands still or walks or slides or jumps. Or while doing that, he jumps and attacks and slides and attacks, stands still and attacks. Or maybe he has a special attack or an alternative attack. So this kind of has a ton of features or states already that are pretty common in like platformers or brawlers. So and if we look at those dimensions, we would only need like 8 movements, 3 attack states, and that would be a total of 24 values we need to encode, and that is like a lot less than those 256 values we can encode in 1 byte. So that is the same idea again. Maybe we would have another dimension. Let's whatever, you know, like eating, like maybe eating a burrito, you know, and this guy is like, this character is so incredible. He can fight with one hand, have a sword in one hand and a burrito in the other one, so he can fight, walk, and eat at the same time. If that was your game, you would have another dimension, yeah, of eating, you know, maybe eating or not eating, yeah, or maybe has special foods that he eats or whatever. So all of this stuff you can add more dimensions, but we'll just stick to 2. But as you can see, it's like multiplicative, so it grows like exponentially. The more dimensions you have, and things can get complicating. But going back to this, like we had the circle where the dimensions would be the rings and the slice, and we could just have like, we can also think of it as we have our attack, our no attack, and we have our special attack here. And then we would have our like jump state and crouch state, and move to the left, move to the right. I'm sounding like a song already. And so on. So you would have like for every state, you would have a number. So this could be number 0, number 1, number 2, number 3, all of that stuff, up to 256 or 255 in this case, if we start with 0. So this is the basic idea. And if you would add another dimension, this would become basically a cube. Like if eating would be another thing, like eating and not eating, and so on. You kind of get the picture. Things get more complex, more confusing. So you kind of have to figure out what makes sense for you. But instead of just thinking of this circle, you can also think of it as a rectangular or a cube with different dimensions. So yeah, and yeah, how you would do it in that case, you would probably like create like some kind of index with all of those values, and you basically kind of do the same idea. Just in this case, you have very specific states that are very different, that are not comparable. They're not like an angle, like a number of slices, which are all basically the same, just different. But they are very distinctly different. So we can't like think in that metaphor anymore. They have kind of distinct values. But I think you kind of get the idea. So that is what I wanted to talk about in the end. So you have a kind of bit more broader idea how we could apply those kind of techniques into creating a really efficient encoder and decoder. Yeah. So that is it. I hope you enjoyed it. Leave some comments down below. I was also thinking of making a custom networking video for Godot, because you're not going to use your RPC functions for that, or maybe you could, I'm not sure, but it kind of defeats the purpose if it's not very efficiently packed. So yeah, let me know if you want to see a video like that. And that's kind of all. Thank you very much, and see you in the next one.